Hello! This will be a demonstration of Proposition 19 from Book 9 of Euclid's Elements, which says given three numbers to investigate whether it is possible to find a fourth proportional to them. We're given three numbers A, B, and C, and the task before us is to investigate whether it is possible to find a fourth proportional to them, such that A is to B just as C is to this number. If such a number exists, then there is a fourth proportional to A, B, and C, but if it does not exist, there is no fourth proportional to them. I will say before I go through this demonstration that this is not Euclid's version of the proposition, but rather one which I wrote myself, or at least I wrote it independently. The reason I've done this is because the original text of this proposition is, quote, hopelessly corrupt, according to Sir Thomas Little Heath, who is the most prominent translator of the Elements into English. I have looked at the original text of this proposition, and I would agree with Sir Heath. It's not very good. It distinguishes between far too many cases, and the logic is just, it doesn't work. I really don't believe that Euclid wrote this himself. So what I've done instead is I've created a version of the proposition that is my own, but which successfully demonstrates it as opposed to the original text. With that said, we'll go into the demonstration. Now, our three numbers, A, B, and C, they are either continually proportional and the extremes A and C are prime to each other, or not. And what I mean by or not is not that our three numbers A, B, and C are not continually proportional and that A and C are not prime to each other, but rather that this information is not given to us, it is not privy to us. If first we know that A, B, and C are continually proportional and A and C are prime to each other, then we know from Proposition 9.17 that there is no fourth proportional to them. For that proposition, 9.17 tells us that if numbers be in a continued proportion and the extremes be prime to each other, then the last number is not to any other number, just as the first number is to the second. Or in other words, if a continued proportion has extremes which are prime to each other, then it cannot be extended any further. So if A, B, and C are in a continued proportion, and the extremes A and C are prime to each other, then we know Proposition 9.17 tells us that there is no fourth proportional to these numbers. But say that we don't know this information. What we can do is this instead. We're going to create the number D, and the number D will be the product of B and C. So B times C makes the number D. Now, it is either the case that our first number A measures this number D, or it does not measure it. If it does measure it, then let it measure it according to the number E. E will be the number according to which A measures D. Or in other words, A multiplied by E makes the number D. But we also know that B multiplied by C also makes the number D. So we have two products which make the same number. So common notion 1 tells us that they will be the same, they will be equal to one another, so that the product of A and E is equal to the product of B and C. Now we can turn this into a proportion according to Proposition 7.19 and say that A is to B just as C is to D. Now it is obvious from this statement that A is to B just as C is to E that there is a fourth proportional to our three given numbers A, B, and C, and that it is the number E. So not only have we investigated whether it is possible to find a fourth proportional to A, B, and C, we have found that fourth proportional. It is the number according to which our first number A measures the product of our second number B and our third number C. But say the number A does not measure the number D. Then what we want to prove from this is that there is no fourth proportional to A, B, and C. For if there were such a number, we'll call it the number E. E will be a number such that A is to B just as C is to E. Now it follows from this that A is to B just as C is to E. It follows from this, from Proposition 7.19, that the product of A and E is equal to the product of B and C. That is to say, equal to the number D. We know that the product of B and C is the number D, so if the product of A and E is equal to it, it'll also be equal to the number D. But from this, that A multiplied by E makes the number D, it obviously follows just from the definition of multiplication, definition 7.15, that A measures the number D according to the number E. But this is contrary to the hypothesis of this case, which is that A does not measure the number D. So if there were a fourth proportional to A, B, and C in this case, then the same number A both measures and does not measure the same number D, which is obviously impossible, and so we can conclude that there is no fourth proportional to A, B, and C. And by now we've successfully investigated whether it is possible to find a fourth proportional to A, B, and C as we've gone through all the possible relationships that A, B, and C have to one another. So having done all of that, we are therefore done with the proposition, therefore, etc., Q, E, D. You might have already noticed, just from how this proposition is laid out, that it is simply a special case, or that the previous proposition, rather, is a special case of this proposition. If you want to find the fourth proportional, right, you take the product of the second number and the third number, and you divide it by the first number. That's how we made the number E. We took the product of B and C, divided it by A, and we got E that way, and E would be the fourth proportional. But in the previous proposition, 9.18, which was about finding a third proportional, it's a special case of this proposition in that the second and third number are simply the same number. Because to find the third proportional to two numbers, say A and B, A has to be to B just as B is to this other number. So you could say that this number is a fourth proportional to A, B, and B. You also, of course, notice that if you do the product of the second number and the third number when they're equal to each other, that's simply the same as taking the square on the second number. So that's another way in which the previous proposition 9.18 is just a special case of this proposition 9.19. Before I close out the video, I do want to go through a few examples, just going through the three different cases of this proposition. Say we have three numbers, 4, 6, and 9. And we want to know if there is a fourth proportional to these three numbers, 4, 6, and 9, such that 4 is to 6, just as 9 is to this other number. Now, our first question is going to be, is this a continued proportion where the extremes are prime to each other? Is 4 to 6 just as 6 is to 9? Well, yes, this is the case, that they're both just as 2 is to 3. We also want to ask if 4 is prime to 9. Now, this is clearly the case. So it follows from this fact that 4, 6, and 9 form a continued proportion, and that 4 and 9 are prime to each other is, at least according to proposition 9.17, that there is no fourth proportional. There is no number such that 4 is to 6 just as 9 is to this other number. But say we don't know if our three numbers form a continued proportion where the extremes are prime to each other. Say instead we have three numbers, 4, 5, and 8. Now, our first question is going to be, do these form a continued proportion where the extremes are prime to each other? No, this is not the case. 4 is not to 5 just as 5 is to 8. Furthermore, the extremes 4 and 8 are also not prime to each other. So, what we're going to do instead is we're going to take the product of the second number 5 and the third number 8 and divide it by our first number 4. And we would get, in that case, 5 multiplied by 8 is 40. Now, does 4 measure 40? That's going to be our next question. Does 4 measure 40? Well, obviously it does, and it measures it according to 10. So yes, we can say that there is a fourth proportional to 4, 5, and 8. Furthermore, we also know the exact number it'll be. It'll be the product of 5 and 8 divided by 4. That is the number 10. But say instead we have numbers 4, 5, and 7. Let's ask the same questions. Do these form a continued proportion where the extremes are prime to each other? Well, 4 and 7, those two numbers are prime to each other, but 4, 5, and 7 do not make a continued proportion. 4 is not to 5, just as 5 is to 7. So we're going to ask the next question. If we take the product of the second number 5 and the third number 7, does our first number 4 measure it? Well, 5 times 7 makes the number 35. So does 4 measure 35? And no, it does not. And so we can conclude from this proposition that there is no fourth proportional to 4, 5, and 7. 4 is not to 5, just as 7 is to any other number. Now, just like last time, the reason we have to do this sort of proposition before finding the fourth proportional, whereas the previous time we saw fourth proportionals, which was proposition 612, that proposition 612 was about finding the fourth proportional straight line to 3 given straight lines. But before we did that proposition, we did not have to do something like this, where we had to investigate whether or not there even is a fourth proportional straight line to our 3 given straight lines. We simply took that as given information and found the fourth proportional straight line. But again, with numbers, we can't do that. And this is for the same reason I talked about at the end of the previous video. It is because you can do operations with numbers, the result of which will not be another number. So let's take our last example of 4, 5, and 7. Now, if we didn't have this proposition and we just went straight ahead and took the product of 5 and 7 and divided it by 4 to take a fourth proportional, we would end up with 5 and 7, that's 35. 35 divided by 4 is just 35 divided by 4. You have to leave it like that, because 35 divided by 4 is not a number. Again, not in the Euclidean sense, or what we would say it is not a natural number. Rather, it is a ratio. And so what Euclid would say here is that there is not a fourth proportional number to 4, 5, and 7. Because if you do this sort of multiply the second number by the third and divide that product by the first number, you don't end up with another number. So the reason we have to do this sort of proposition about investigating whether it's even possible to find a fourth proportional is for that same reason, because you can do operations with numbers that won't always result in another number. With that said, I don't have anything else to say about this proposition, so I'll end the video here and move on to proposition 920.